Welcome to In Building Solutions Distributed Antenna System Dash webinar. So in this webinar, we'll talk about these main topics. First of all, we'll go through RAN introduction. So we'll see what are the various parts of RAN and how RAN evolved from 1G to 5G. Then we'll talk about what is IBS, in building solutions. Why is IBS important, right? And then we'll talk about IBS system requirements. What are the coverage requirements, capacity requirements, and the interference requirement. Then we'll go through buildings architectures. So we have various kinds of buildings. It can be stadium, hospital, underground railway stations, tunnels, etc. Right? So we will talk about what are the various characteristics of those buildings and what are the unique requirements of each building according to DAS, right? Then we'll talk about, we'll go through repeaters, small cell, leaky cables, and in the end, we'll see what are the types of DAS, like active DAS, passive DAS, and the hybrid DAS. Right? So as I said, there are various types of DAS, right? Like leaky cable, active DAS, passive DAS, and the hybrid DAS. So one thing that it's important that the radio designer should know the basics of all the various types of indoor coverage distribution solution, because in many projects the best solution will be combination of various types of distribution hardware. And good indoor radio planning is all about well equipped toolbox. So suppose if you have only hammer in your toolbox, yes, and hammer can solve many of your problems, but only hammer in your toolkit will limit your possibility, right? So indoor radio planning is not about using one approach only. So learn the pros and cons of all the various types of designing indoor coverage, and then you will know what is the best approach for design at hand, right? Because often the best approach will be the combination of different solutions. 5G course, right? So are you with me? So if you are with me, then please write yes in the chat box. Okay, then let's move next slide. So this is a list of abbreviation we will use here. So let's move to the wireless world. So to set up the stage, let's talk about the mobile network coverage, right? I know everyone must know about it, but we must revise it before jumping to the IBS because it will act as our base. So radio access networks. So they are commonly known as cell sites as well. So these are the strategically placed to provide wireless coverage to users within a specific geographical area. You can see it all around you, okay? The placement of radio access network or RAN components is critical to ensure that users have reliable connection. So when you are planning the deployment of a radio access network, network operators consider various factors to design for coverage and the capacity. Factors can be, you can say that like population density, it can be related to topography, it can be related to building density, it can be related to traffic pattern, right? So there can be many factors. So by analyzing these factors, network operators can determine the optimal location and the configuration of RAN. The ultimate aim is to ensure maximum coverage and the capacity. So like for example, in urban areas with high population density, network operators may need to deploy more cell sites with lower output power so that each site can provide coverage to smaller areas. But we need large number of sites so that we can cover our high population density. But in the rural areas with lower population density, network operators may need to deploy fewer sites with higher output power to provide coverage to larger area. Okay, so thousands of radio access elements create seamless coverage and the mobility. So whenever you want to go from one place from like Virginia to California, so you will have a seamless coverage. So you will not make a drop call, right? So wireless telecom system. Okay, so wireless telecommunication systems components are composed of three main components or parts. So we have user terminal, right? So examples can be smartphones, tablets, laptops, and other mobile devices. Basically, any kind of wireless devices. The user terminal is connected to RAN wirelessly, or you can say through the air interface. So the RAN is responsible for providing the wireless connectivity required for mobile device. So the radio access network includes different parts like you can say antenna system, then it can be radio, or you can say RRU nowadays, or it can be baseband unit, right? So RAN consists of mainly three parts: antennas, radios, and BBUs. Yes, it will include CPRI also, but that may not be considered as a component. Okay, so these two are connected through an air interface, and we are using a wireless connectivity. And the radio access network is also connected to the core network. So the core network is responsible for managing the overall operation of the network. So there are different means to connect the core network and the radio access network. So these can be connected through microwave, wirelessly, or physical cable, or the fiber optic. And if there is challenge in terrain or large distances, you may use a satellite to interconnect this. So example can be connection to ships, aeroplanes. So most of the time they use satellite for wireless connectivity. Okay. So these are the main components of a wireless telecom system. And you have the user terminals connected to the radio access network and the core net. So have you ever stopped to think about how your mobile device or cell phone is able to connect to the internet? How you are able to make calls and text while you are on the go? It's all thanks to radio access network that is all around you. Okay. So next time you're out, take a look around. So you will likely see cell towers and antennas on a top of a building, along the side of a road, and even in the mountain, or even inside the malls. So this type of antennas are inside the mall, and we call it the in-building solutions. Okay, IBS. So some people call it Wi-Fi access point, but it is not the Wi-Fi access point. It is an omnidirectional antenna, or sometimes an active antenna that belongs to the radio access network. Okay, so we'll talk about this in our today's session. So what is radio access network again? So this is the part of the wireless telecom system that is nearest to the subscribers. Okay, so you see it all around you. Okay, so you can see it in the malls, you can see it on the mountains, rooftops, wall mounted on a building. The location is widely distributed, so you can see it everywhere, since RAN creates seamless coverage and mobility. Okay, so RAN is all around you. Okay, so what is radio access network? So as you know, RAN has evolved from first generation to the fifth generation, and each generation is improving upon the last. But essential components are the same. We have antennas, so these convert electromagnetic signals to radio waves and the vice versa. And then you have radio unit. So radio unit act as a transceiver. They transmit and receive the user signals to the base station and the vice versa. And third one is the baseband unit, and it is used for signal processing, network access. So this component processes the signal. It contains software and hardware to do that, and it makes wireless communication possible over the radio waves. Okay, so this is how RAN evolved from 1G to 5G. We have discussed in detail in our last webinar as well, but you should know that first of all, we have 1G, that is analog system. Then we move to 2G, that is digital system, and then 3G, which is the foundation of mobile broadband, and 4G, which is further enhanced mobile broadband. And then we have 5G, which has many new cases. If you know that, we have EMBB, right? We have URLLC, and we have MMTC, right? So we have EMBB, URLLC, and MMTC. So many cases are introduced in case of 5G. And you should also know the names of various RAN generations as well. So in 2G, we call it GE RAN. Okay. In case of 3G, we call it UTRAN. In case of 4G, we call it EUTRAN. And in 5G, we call it NG RAN, right? So this also we have covered in our previous session. So please go through, because I'm not going in details of these topics, but at least you should know the names. What are the RAN technology name in case of 4G, 5G, 3G, and 2G. And you should know the basic function of baseband unit as well. So BBU is typically located below the tower in the traditional network. And this is responsible for providing the processing of the baseband signals. And it is placed in the equipment room in the traditional network and connected to RRU through an optical fiber, right? I'm talking about traditional, and these are the basic functions of BBU, and we don't have to go in detail. So when I share the PDF, you can read these things, like the BBU main components and functions can be DSP, forward error control, modulation and demodulation, channel estimation, and the radio resource management. And then we have this remote radio unit. So this is how RU look like if you have not seen it before. So, and main functions of RU, it acts as a transceiver, transmit and receive the user signals to the base station and the vice versa. And then we have this CPRI, right? So this is called the Common Public Radio Interface. So it enables the high-speed transmission of data over a fiber optic cable. It allows the RRU and the BBU connection. So this is the Common Public Radio Interface. And nowadays, it is not necessary that baseband is near the tower. Baseband can be centralized location as well. So SIPRI is an interface that sends data from RRU to the baseband unit, and it is a serial interface which is very high speed connection. Basically, it's a way to translate all those radio signals back to the computing function. And just to let you know that there is a new thing introduced which is called eSIPRI in case of 5G. For your information, like SIPRI is TDM based and eSIPRI is packet. Okay. Then let's see the evolution of RAN. So RAN is a critical component of the wireless communication. It provides coverage and connectivity to the mobile device. And there are several RAN architecture available. So there are several RAN architecture available today, and each of them have a unique strengths and the trade-off. The choice of RAN architecture will depend on the range of factors. So it may depend on the specific use case or the network topology or available resources or the performance requirement. So operators can optimize their network performance. So in the RAN evolution, first we have seen that we have this traditional network. So this is the traditional RAN architecture. So this is the traditional RAN architecture that has been used for many years for technology like 2G up to LTE. Okay. So it consists of separate baseband and radio units, which is connected through dedicated fiber or the copper cables. So the cell sites are the baseband and the RRU are located in the cell site premise, and it has various version like non-split, right? In non-splits, RRU and BBU are co-located on the site. Then you have this split version where RRU and BBU are connected by the SIPRI, and BBU RU interface are the proprietary, right? So same like this here, baseband units, radio units are located inside the premises of the cell site. And this is non-split scenario, right? And then it evolves to the centralized network. So it emerges because we have need for more flexible and cost-effective solutions. So it uses a centralized process. You need to support a multiple remote radio heads, and these are connected by a high-speed fiber optic links, right? So this approach can help to reduce cost and improve the network efficiency. And then it becomes the virtualized network. So virtualized network builds on the benefit of CRAN. Actually, it is CRAN as well, but it adds the virtualization technology. Okay. The idea is to further improve efficiency and the scalability. And then we have this Open RAN. So the Open RAN, now we have the core network, but your baseband is now separated into centralized unit and the distributed unit. And then you have the radio unit. Okay. So there is separation. The functionality is already split. And then the cloud native function, the GPP hardware, meaning you are also using a general purpose hardware or the CORDS hardware. And the software defined networks and the interfaces are open, meaning you can mix and match different vendors to the different vendors of the RU to the CU or the DU. Okay. So this is how the Open RAN is different from the virtualized RAN. Okay. So you remove the proprietary equipment. This is how the Open RAN differ from the traditional RAN. And then we have this Open RAN or 5G architecture and the new interfaces. So you should also know the name. So between CU and the core, we have the backhaul. Between DU and CU, we have F1 interface. In case of user plane, we have this F1U. And in case of control plane, we have F1C, right? And then between DU and RU, we have this front haul connection, or you can say it is connected through the eSIPRI. And function of all these things, RU, DU, CU, core, or cloud, we have discussed in our previous session as well. And this also we have discussed that we should know the layers, which are the protocols. So for remote unit, main protocols used are lower physical layer and the RF. And for distributed unit, we have RLC, MAC, and higher physical layer. And for centralized unit, we have RRC and PDCP for the control plane, and SDAP and PDCP for the user. Okay. Then we have this different RAN structure. So the radio access networks comes in the different form. So when we say different form, it is either an outdoor or an indoor solutions or a different kind of structure. So we have different form of radio access network in terms of their structure. So we have this kind of outdoor solutions like SST, which is also called self-support tower. Then we have this rooftop site, and then we have these guide towers. So what is guide tower? A guide tower or guide mast is a tall, thin, vertical structure. And why it is called guide tower? Because it depends on the guide lines. It requires guide lines to stay upright to resist lateral forces like wind loads or heavy winds, right? And then we have these emergency sites, or we call it the cow, the cell sites, the cell site on the wheels. And then we have these monopole towers. After that, we have these camouflage sites. So what is camouflage tower? So camouflage tower means any tower that due to appearance hides the presence of the tower. And then we have what you call wall mounted site, and lastly the private net. So now the question comes, how does a radio access network provides the mobile coverage? So this is a typical area where we want to have a mobile coverage, meaning we want to have a signal in our telephone or the mobile phones, right? So we need to build these kind of structures. So this is a typical example of outdoor radio access network. When we powered up this outdoor radio access network, it will give us the mobile coverage. So the colors that you have seen are the indicators of how strong will be the signal if you build a radio access network in that particular area. For example, this dark blue, right? This dark blue will be the areas where coverage will be the full bar. Okay, so you can see that we have signal maybe more than -75. But if you go further from the side, you will have some another shade of blue, maybe light blue, right? But if you go indoor, you will have the another shade. You will have another kind of signal level. It may be neg 95, neg 105, or so on. So getting far away from the radio access network or cell site, our signal level or the received signal level goes down, right? So this is the main principle. So it is a combination of distance from the site and the path loss. Okay, so how the obstruction in the area, where are you located, indoors or outdoors, population, topography. So these factors will affect the signal strength. Okay, so now the question comes, where are the users? So users are everywhere. So they move, they're in the offices, at home, maybe at the port of entry of railways, airports, shopping centers, and all these things, right? But they are mostly inside and rarely outside. So now the question comes, how to guarantee sufficient coverage level inside of the building? Is the macro cell level is enough to penetrate inside buildings? And we should also know that how do radio waves travel and behave inside the building, right? Okay, so you will see again, building, malls, hospitals, other establishments. So if you deploy a typical macro site, it is not enough to cover big buildings inside. It is not enough. So you can design an antenna pointing towards the building, but most of the time it is not sufficient. So IBS is one of the effective ways to solve this problem in the indoor in terms of coverage, capacity, and the quality. So, okay, you can see here. So these are the areas, right? So these are maybe some buildings here. So these are the areas in the populated region of this map. So it seems that there are weak signals, especially if these are passing through indoor or a building structure. Okay. So why it is like? Because the electromagnetic energy, or you can say RF signal, is being blocked. Okay. So due to walls, it tends to get weaker. Okay. So what is the impact of the obstruction and the structures on the electromagnetic energy? So that's why there is a limitation on the wireless signal. So to cover population in the building, we need some better solution. So the better solution is called the in-building solution. So what is the in-building solution, or what is IBS? So this is the cellular service inside the building to provide better coverage, capacity, and the quality. It uses a distributed antenna system, or DAS, distributed antenna system. So you are distributing the antenna in the entire building. So what's the purpose? Now the purpose is to evenly distribute the signals in all the target area. So this is all about RAN and the IBS. Now we'll go deep in the IBS in the next few slides. Okay, so let's move to the next part, in building wireless world. So what is IBS? In building solutions. So cellular service inside the building to provide coverage, capacity, and the quality. And it uses DAS, distributed antenna system, to evenly distribute signals in all the target areas. So why is in-building coverage important? So as I said earlier, that 80% of the calls and data sessions are initiated indoors. So why it is important? So let's take one typical example. Let's divide our normal 24 hours. So just imagine from 12 to 6 a.m. Look, we have 7 hours. So probably you are sleeping or preparing yourself to the work. So that is 7 hours, or you can say 29% of the 24 hour in a day's lives. Okay, and then maybe 1 hour travel, so that is 4% outdoor. And then when you go to office, work in the office, so you will have like 8 a.m. until 7 or 5 p.m. So if you're like that, your boss will not ask you to do some overtime, So that is 10 hours already. And that is equivalent to almost 42% of your 24-hour life in a day. Okay. And then you go out again. So you will travel probably 2 hours stuck in traffic from 6 to 8 p.m. And that is equivalent to 8%. And then again, you go to your office, rest, watch Netflix or doing some online courses. So you will have this 4 hour. You will spend 4 hours in your house. Like whenever I come back home, at least for 2 hours, I try to study new things, new technologies, maybe in building, ORAN, cloud, whatever, right? So I spend at least 2 hours studying every day. So, and then you sleep. So that is equivalent to 17%. So if you see the typical life of a professional, just 12% are spent outdoors. That's why we need in-building solution. So again, if we take one more example, you can see here, if you have line of sight, you will have good coverage, right? So this person has a good coverage. But if you go indoor, now that start of bad coverage, right? So if you go inside, so this lady may get the bad signal. So that's why we need indoor. That's why in building coverage is important. So as you know that you may be served by one sector or one cell resources, but you are not only one that is served by that source or sectors. That's why in building solutions are very important. Okay. So people are concentrated inside the building and different establishments where most of high traffic are generated, voice and data. Overall, if you put IBS, the subscriber experience will be impacted. That's why it's very important. Now it's very important to have in-building solutions to improve the operator's revenue, right? So just think, when you do not have a good capacity and the quality, you will not browse much. You open one app and if it is not opening quickly, you just kill the application and put the phone back in your pocket. So now just think the change in the behavior of your subscribers when you have a good coverage and the capacity. So you motivate to watch YouTube, Netflix, high definition videos, right? So people will start to browse the internet. So they will try to open their social media and watch some videos there, right? So we call it traffic. So just imagine how big will be the revenue if you deploy an IBS site in an area. So you can see that when there is no IBS site and we have only macro, so traffic increase from here to here like this, and we have this much traffic at this particular moment when we don't have IBS. But the moment we put IBS, our traffic increase from this point to this point, right? But in the end, as the time goes, our traffic increased like this, right? So earlier we have up to this point and then it increased to this point. In the graph, it looks like that our traffic increased 2 to 3 times as compared to macro outdoor cell when we install our IBS cell site, right? So that's why it's very important that before deploying an IBS site, one should do deep analysis in terms of the business case, because the cost of deploying an IBS site is very high. Okay. So it's not only the equipment, it's not only the services, but the acquisition, okay, the cost of the design, okay, and the implementation and also the optimization. So many things involved here. Okay. So let's move to the in-building tool. So one of my favorite tool for in-building design, planning and everything is IBWave. So IBWave is one of the best tool for in-building, and IBWave is a global provider for innovation in the building wireless software solutions. The motive is to help operators, system integrators and the equipment manufacturers better design and plan the multi-technology wireless network inside the buildings and the venues. And IBWave is a global leader at innovating and the delivering the software solutions. It keeps the world connected with simpler and the faster designs for in-building wireless networks. The great point is that these designs are quite affordable, right? And it has maybe 1,000 companies worldwide who can trust this tool, IBWave. And I'm using this tool for many, many years. And if you think that one thing I can't survive in building design and planning, that is IBWave. And it support all phases in the network design, be it survey, dimensioning, engineering, install, commission, and the operate and maintain. So because it has various devices like IBWave Mobile, IBWave Design, IBWave Unity, right? So it has IBWave Design, Unity, Mobile, and Wi-Fi. And it has various optional modules like propagation, optimization, and the collection. In short, this is the best tool for in-building design, planning, and the optimization. And I'm using it for many, many years. It makes my work so much efficient and the productive. And then let's talk about the building architecture. So where do we need to deploy IBS? Can you please write in the chat box where you need IBS. Okay. Thanks for the right answer. So here are the few examples you all mentioned in the chat box. So let's talk about things to care in the IBS system in the next slide. So where do we need IBS? It can be offices, industries, airports, tunnels, high-rise buildings, hospitals, hotels, and the stadium. And there can be many more examples. Okay, thanks for the right answer. So here are the few examples we have discussed. And now let's talk about things to care in the IBS system. So first of all, we have to think of the RF requirements. So first of all, we have to think what kind of technology we are going to deploy, be it LTE, 5G, 3G, or 2G. But normally we are talking about LTE and 5G nowadays. So what kind of frequency band you are going to use? Be it 800, 700, AWS, millimeter waves, 28 gigahertz, 39 gigahertz. So this question you should ask. And then we have to think of integration. What kind of operators we are using? Is it single operator solutions? Is it multi-operator solutions? Is it like single technology or the multiple technology? And but because the later is particularly important for multi-operator, multi-technology design, because sufficient agreement among all parties must be established and a perfect coordination should be arranged at all times, be it during the design process, installation process, commissioning process. The aim is we should guarantee that performance is not affected for any of the participating operators. So these are the RF requirements. Apart from RF requirements, so in building design should have some building specific. It may be related to aesthetics, that color of cable, color of antenna should match our walls and our buildings. Then we have this cable types. So we should think of the rigidity, diameter, and fiber retardant compliance. We have to think of the working arrangement as well. Also, physical aspect design like heat, power supply, and the cable stand. So as the building is going to be modified in certain way, so we should also communicate properly with the building owner and operator for their specific requirements. For example, a very critical aspect can be where to put the antennas. What's the antenna's location where we can put? An RF expert may have some optimal solution for antennas to maximize the coverage, capacity, and the quality. But building owners may not agree with such installation since it may affect the aesthetics or the certain spaces, or it may be difficult to install antennas there, right? So compromise should always be made between owner, operator, and the building and the DAS installers, right? Now let's talk about different characteristics of the building. So we have seen different types of building where DAS can be utilized to improve coverage and the capacity, like stadiums and the ballparks, casinos, hotels, airports, office buildings, shopping centers, theme parks, right? So now let's talk about the characteristics of different kinds of buildings. Each building has a unique property. By knowing them, it will be very easy to design that particular venue. So in addition to RF requirements, we must consider some relevant issue as well, which are dependent on the nature and the type of building. So what are the common RF signal propagation inhibitors? Can you write some of the issues we face for wireless while signal travel from one place to other? Okay, so thanks for the right answer. So as you know that radio signals are electromagnetic waves that travel freely through the air, and they can be absorbed, refracted and diffracted by various materials. But after 9/11, we have stricter building codes for metallic qualities in glass and stronger steel supports to new buildings. So we may have issues related to line of sight issues, dense tree cover. We may have issues related to metro downtown and neighboring buildings, dense construction materials like glass, steel, blocks and bridges, dense interior walls, and the furniture scheme. In addition to that, we have issues related to underground structures such as basement and the military bases. So these are the common propagation inhibitors, right? So let's talk about issues in different kinds of buildings. So first one is the high-rise building. So for high-rise buildings, first issue is related to interference. Since they have direct line of sight from a macro site, this can interfere with our IBS solution. Also, since these facilities have large number of floors, coverage, so handover inside the elevator is important. And data rate should be distributed across the building, especially at the higher level for the office spaces. In addition to that, aesthetics and the future capacity demands as the number of users inside the building grows is also very important. So you have to think of that as well. The second important kind of buildings are the airports. So airports is a place where we can congregate a very large, a very high density of users. So it is especially important for operators who can capitalize on roamers arriving to the country. The problem is that airport layout is very challenging. It has very little number of floors. It may not have like 20 floors or 50 floors, but the problem is that the floor area is very large, right? And it may have challenging propagation spaces like atriums, right? So sectorization is important for airports, as well as proper design for handover areas with low subscriber density. And we should guarantee the handovers with the outdoor cells as well. And in the case of airports, we have to take care of tarmac as well, right? It is also called ramp and it is also called apron as well, right? And this is the photo of the Vienna airport. And I once went to this city and this airport. And this is my one of the favorite city in the whole world. If I given chance, I will stay my whole life in this Vienna city, right? In Austria. Okay, let me write Vienna Airport, Austria. And then we have these road tunnels. So in general, only coverage at low capacity is required in the road tunnels. Thus, the solution for road tunnel structure is achieved using repeaters or maybe any kind of low power BTS. So interference is very low in these cases, but handover is very important because cars can come at high speed, low speed. So handover is very important in case of road tunnel. Then we have these metro tunnels, or you can say underground tunnels. So they have similar requirements as compared to road tunnels, but in addition to that, they have capacity requirement as well, because we may have stations where large number of people congregate, right? So coverage level plus capacity is important in the metro or the underground tunnels. And then we have sports stadium. This is one of the most complex dash design we can do, and it has high peak capacity requirements and all things related to dedicated coverage, right? And I will give one more complete session on sports stadium design, maybe next week or maybe next few days. So a sports stadium is one of the complex. So we have to talk in detail of sports stadium in the complete session. Okay. So next topic is types of IBS. So there are several types of IBS solution possible. It can be repeaters, it can be small cells, it can be passive dash, it can be active dash, it can be hybrid dash, it can be leaky cable, and it can be RF over 5. So there can be many other solutions possible, but in this session, we'll talk about all these solutions like repeaters, small cells, leaky cables, passive dash, active dash, hybrid dash, and the RF over 5. Okay. So this is the basic concept of dash. So once a radio signal is inside the building coming from a donor outdoor cell or through a dedicated pico cell, it must be distributed across the building. So a dash splits the transmitted power among several antenna elements installed in the distributed environment, separated in space, so to provide coverage over the same areas as a single antenna, but with a reduced total power and the improved reliability. So this is possible because less power is wasted in overcoming two things. One is penetration, and second one is shadowing. So due to which our line of sight present is more frequently, right? Our LOS is more frequent, then due to which our coverage is improved, our SINR is improved, and because we have less fade depths and reduce the delay spread. So this is the basic concept of the dash. So as I said, there are various types of dash. We'll talk in detail all about these types of IBS. So, but in this slides, let's talk about what are the names of different types of IBS. So it can be repeaters, it can be passive, active or hybrid dash, it can be small cells, it can be leaky feeders, right? So let's talk about our first solution, which is repeaters. As I said earlier that it's important for radio designer to learn the basics of all types of indoor coverage solution possible, because indoor radio planning is not about using one approach only. We should know the pros and cons of all the solutions possible, because only then we can have efficient solution. Our only aim is that we should give the best solution possible in the least amount of money used, right? So we should learn all kind of solution possible in case of IBS. So first one is repeaters. So when we say repeaters, it means signal is amplified, right? It's like an coverage amplifier or the coverage extender, right? So this is a coverage amplifier, or you can say coverage extender, right? So it extends your coverage. So you can see there is an existing outdoor site, right? So this is an existing outdoor site, right? And existing outdoor site feed this particular antenna. So we call it donor antenna, okay? And then it will feed to an amplifier. So here we can use one amplifier. So here they are feed to an amplifier, okay? So what happens here is that there is an improvement in the coverage because it will amplify the signal and then you will distribute the signal inside the building, but a source in an existing outdoor site. So it will improve your coverage inside the building, but there will not be any improvement in the capacity because you are using the capacity of the macro site only. You are just using the capacity of the macro site. So in-building repeaters are the active devices used to overcome the path loss between the macro cell and the in-building uses. Why? Because due to high losses produced by the walls and other buildings partitions, it may not be possible to penetrate those walls. But with the help of this repeater, we can penetrate those walls as well because we have better line of sight with the help of those dash antennas. And the idea of providing coverage using a repeater is to use a highly directional antenna called a donor antenna pointing to serving macro cell site. The downlink signal is amplified in both directions. That's why I call bi-directional amplifier because signals are amplified uplink as well as downlink, right? So the downlink signal is amplified in both directions. On the other hand, uplink signals for each mobile users are amplified through the bi-directional amplifier and sent back to the donor site with the help of this donor antenna. Okay. So what are the major applications of repeaters? So the repeaters are used to extend coverage to weak or the unserved areas in places where dedicated capacity is not required. In other words, the use of repeaters can be seen as a means of distributing available capacity, right? So it will improve your coverage, but not capacity, right? So capacity will not be improved by the repeaters. And what are the various advantages of repeaters? So the use of repeaters to provide in-building coverage is very popular since it involves low acquisition and the operational cost. And the technique has also provided to be reliable for extending coverage and also to create a dominant area, right? Because it improves the quality of signal. And what are the some issues that must be taken into account while designing in-building using repeaters? So first of all, we have to take care of this bi-directional amplifier gain, right? So gain must be chosen to combat signal losses through distribution in a dash, right? And additional losses due to splitters and taps should be also look up during our link budget stage, right? Then we have to take care of our noise floor level as well. So there is noise increase due to loss in a BDA. So special care should be taken with noise floor level in both sides of the BDA. And then we have to take care of automatic gain control as well for repeater solution. And then placement of BDA is also very important. And it is recommended that it should be placed as close to the donor antenna as possible because then we can minimize our losses, we can minimize our noise factor. And as I said earlier that a repeater can extend coverage inside the building, but at the expense of stealing capacity from the donor macro cell. So it's a good solution when you want to improve your coverage, but it's not a good solution if you want to improve your capacity as well. So for capacity, it is not a good solution. So here is one example of node A. So one example of repeater. So this is the example of like node A. So that is coming from CommScope. So the picture is taken from internet. So it has various features, but two important features I like is that it supports up to 4 frequency bands, or it can support 4 operators, and it is available both in the medium and high power class. Okay. So this is the one example of repeater node A from the CommScope. So if you go to internet, if you go to Google, you can just type node A CommScope and you get all the details of this repeater. So you can see that it has various components like full band RF card, and it is available in both medium or high power options, right? It has main power and it has integrated multi-band combiner and the modem. So let's jump to the small cell. Now let's talk about small cell. Okay. What is small cell? So a small cell is a mini base station, specially designed to extend the data capacity, speed, and efficiency of a cellular network. So these low power radio access nodes can be deployed indoors or outdoors, and they usually have range from 10 meters to a few kilometers. And mobile operators use small cells to extend their service coverage as well as capacity. And their smaller range enables operators to use the same spectrum at the short distances, and therefore significantly increase the network efficiency. So according to report, at this moment, there are around 12 million small cells deployed across the globe. And this number is forecasted to increase up to 70 million by 2025. So you can see that the job market may also improve. So if you have a knowledge of small cell, then it can help you to get a good job or promotion in your company. So they are an important element of network densification. So they add more base station connected to the existing wireless structure, right? So the small cell will be connected to the core mobile network through the internet. So indoor small cells can be done through broadband, or it can be connected through a backhaul solution. So depending on the specific needs of the customers and the venue owners, small cells can be used to enhance the coverage and the capacity, where a macro tower based solution would either be not feasible or the suboptimal. The small solution is provided to improve signal strength and the speech quality and the coverage. So why small cells? So these reasons we already discussed as similar to DAS. So improve the coverage of signal, improve the coverage in the baseband, improve the capacity, and offloading the macro site. So what are the various types of small cells? We have 3 types of small cells available. One is femtocell, one is picocell, and the last one is microcell. So what is femtocell? So this is the smallest type of small cell that covers the radius of around 10 to 100 meters and can be used in the home networks. So in scenarios where a person has access to high-speed broadband, a femtocell can be installed. The femtocell transforms a high-speed broadband connection into a cellular service that can be used to make phone calls or send and receive SMS, text messages as well. The second one is our picocell, right? So picocell covers the radius of around 200 meters, and the picocells are usually placed at places where there is a high crowd density, like during the festivals, during game in a stadium, concerts, and other large gatherings. So picocells are larger than the femtocells. And then we have this microcell. So microcells are the largest form of small cell that can cover an area maybe up to 2 kilometers, and they are typically used to provide services in the remote areas like villages or in the dense urban. The aim is to improve service at the blind spot caused by the line of sight issues, right? Our DAS, the main function of DAS is improve our line of sight. So users should be in the line of sight as much as possible so that our quality may be improved, our signer may be improved, all this, right? So every small cell is basically a cell on its own. It is a complete base station plus the antenna in one box. So if I write here, so first of all, it has base station plus antenna in one box, right? It is a bit like an access point in Wi-Fi. And every small cell has its own capacity, but it will interfere with all other cells. They are connected to the Ethernet switches, and the switches are connected to a controller. So the controller takes care of the connection to the core network of the operator. And then there is a backhaul, and then it is connected to the core network. So this is the high level architecture of a small cell, right? So these are a few advantages and disadvantages. So it is relatively cheap to deploy, but it has some disadvantages like single operator only, and it has 1 or 2 bands supported on. Right. Let's talk about some of the small solutions. Small cell solution for Ericsson is called R dot. So it is called the radio dot, and it has the similar components like we have radio node, we have switches, we have controller, and then that is connected to the backhaul, right? And all this available is on the internet, so you can go through and just press Google. So in Google, just write R dot Ericsson, and then you will get all those details. And for Comscope, small cell solution is called one cell. So one cell delivers a clear mobile signal through a building of a virtually any size, and this ruggedized radio point extends the signals to the outdoor spaces as well, such as courtyards and the parking lots as well. So it has similar parts like baseband controllers and radio points and all this. And examples can be, here is like RP 5000. So this is a multi-carrier and it can support up to 4 frequency band. Okay. And then we have this RP 2000, right? And it is highly impact and it is used for single frequency. Okay. So these are the solutions. And for Nokia, the solution is called ASIR, Air Scale Indoor Solutions, right? Air Scale Indoor Radio Solutions. So this is so we have discussed for Corning solutions, we have discussed CommScope solution, we have discussed Ericsson solution, and we have discussed Nokia solutions, right? And these are the Huawei solutions as well. And then we have to talk about this leaky cable. So leaky cable is a kind of a coaxial cable. It has an outdoor conductor with the periodic slots. The cable makes part of electrical wave propagated through the cable. So it radiates outside by these periodic slots. The electrical field is almost the circular symmetry and it can be utilized for radio communication to the moving object. The generated electrical field is confined around the leaky coaxial cable. Therefore, the cable can be used very conveniently for the radio communication in the limited locations. Examples can be roads, tunnels, area along the railway or the underground roads, right? So what is leaky feeder again? So leaky feeder cable is also called a radiating cable. So as you know that if we have antenna, right? If we have one antenna, it radiates, right? Antenna radiates, but there is a cable between repeater and the antenna. This cable is not radiating, but in case of leaky cable, the cable is also radiating. Okay, so this cable is also radiating, so it is doing the two functions. First of all, it's radiating as well. Moreover, the leaky figure will also transfer the signal from this place to other. So it is doing the two functions, right? So a leaky feeder behaves like a very long antennas for radios because it allows the signal to reach where it may not be possible without these leaky cables, right? So in circumstances like tunnel works, where it is impractical to install a network of traditional RF antennas, we can use these leaky cables. So when I was working in London, so I was working on this one station called this, let me write the name, Tottenham Court Road Underground. I was working on this project. So it is in London. And so the challenge here was that the staff needed to be able to communicate from underground to above ground, and it should penetrate thick layers of concrete. The solution was to install a leaky feeder antenna system. So installing a leaky feeder allows the staff working underground to have communication with the workers above the ground level, and which is very vital for the smooth running of the underground tunnel. And few years back, I worked on this O'Hare Blue Line station in Chicago as well. Here also, we have used the leaky cables as well. Again, leaky cable is also known as the radiating cable, and this is a cable with many regular slots distributed along the cable. The cable run is the antennas and the radiates cylindrically along the cable axis. The radiation coverage is mainly in the near field, and hence less energy tends to propagate outside building compared to the traditional antenna. Also, leaky cable tends to have more uniform coverage, but the coverage doesn't extend very far from the cable. Generally, leaky cables is passively fed and is compatible with the multiple frequency band. The main difficulty with leaky coax RF distribution is the cable and the connector installation, and it's the associated cost. So what happens? The cables can be large in diameter. So diameter can go up to maybe 1 inch, and so it's difficult to bend around the tight corners. Generally, we use like a half-inch cable for indoors. So leaky cables has some problem related to installation, right? So this is all about leaky cables. So next topic is RF over fiber. So one common type of DAS use a combination of RF and the optical fiber technology. So the RF power from the base station is converted to optical by a main fiber unit, which is transmitted to remote fiber unit. This is our remote fiber unit. So after a signal is transmitted from main fiber unit, the signal is converted to RF with the help of this remote unit. So this allows very low losses between two fiber units, and hence the distance between antenna elements at base unit can be maximized, right? It can be between 2 to 20 kilometer. So what happens is that suppose, so let me write this also. So this is our optical fiber and this is our, you can say, coaxial. Okay. So generally what happens, a fiber cable has generally loss of around 0.5 dB per kilometer, right? So for 2 kilometer, the loss can be around 1 dB, right? For 2 kilometers, loss can be around 1 dB. But for a typical 900 megahertz coaxial cable, the loss can be around 11.5 dB per 100 meters. So for 2 kilometers, it can be 230 dB, right? So for coaxial cable, loss is 230 dB, and for optical fiber, loss is just 1 dB. So fiber systems are therefore commonly used to interconnect multiple buildings separated across the campus, right? And let's talk about the types of DAS. So in IBS, you need to distribute a uniform dominant signal inside the building from the indoor cell using indoor antennas in order to provide sufficient coverage and the dominance. So we can have various options available like passive DAS, active DAS, and the hybrid DAS. So let's talk about the passive DAS. So this is the typical solution of a passive DAS. So when we call passive DAS, it means we are using passive. You do not require power to make it work. So passive DAS system tend to use passive components like coaxial cable, splitters, and the duplexers to distribute signal has no amplification characteristic. So here is an example of passive DAS. So you can see here one remote radio unit, and that is connected to the antennas with the help of this coaxial cable and the splitters. So you can see various passive elements. Splitter is a passive element. You do not need power to operate them, right? Just RF signal, right? So the analysis of feed losses is required for proper coverage. So care must be taken in choosing the cables and power split values so that the correct input power is input to every antenna to achieve required effective radiated power. Large diameter cables should be used in the trunk. So initially at this moment, so large cable or large diameter cable should be used. But more flexible, narrow diameter cable should be used between the jumpers and the antennas, right? So here we should use narrow diameter cable, right? And passive network cables usually run maybe between 500 feet to 750 feet. So that's what they use in the smaller in-building installation, maybe in the range of 100K square feet to, you can say, 250K square feet, right? So this way you can use this, right? And due to increased loss of feed network, the noise floor of the repeaters increased, and hence repeater sensitivity is reduced. So the degradation of repeater noise figure must be taken into account in the link budget as well, right? So noise floor is also one of the important components in case of passive DAS. So these are the basic concept of passive DAS. So the distributed antenna can be implemented using a purely passive infrastructure through a coaxial based component. And a list of components for a passive system varies by design, but usually it has coaxial cable, signal combiners, power splitters, duplexers, antennas, and the attenuators. And these components requires no external power to operate, only an RF signal input, right? And for passive DAS, the base station is located in the central equipment room and is connected through wired or wireless backhaul to the wider network, right? So passive system tends to apply mostly for small to medium sized buildings where coverage is provided by multiple operators in the same building. Multiple base stations are located in the equipment room and the combined together, so that cost of installation of DAS can be shared among the operators. So in this case, it's important to ensure that the combiner provides sufficient isolation among the various operators, right? And we can use different kinds of splitters and couplers so that we can have almost equal power at the end, right? This is one example. So you can see here that we are only using coaxial cables, splitters, and attenuators to interconnect our antennas. So in passive DAS, we should try our best so that we should have uniform equal power at each antenna, right? So we can take the help of couplers, splitters, so that we can have approximately equal power at each antenna. So these are the advantages and disadvantages of passive dash. So passive dash are the cheapest option in terms of hardware. Its architecture is very simple, and since coaxial cables are used, they exhibit a very wide bandwidth. On the other hand, passive dash are much more rigid than the active dash if zoning is required, right? Or if changes to these zones are to be performed, which leads to little scope for upgrading. And losses in passive dash can become so high that they can restrict uplink system sensitive. The installation of passive dash is often difficult to a limited banding cable radius, leading to slow deployment. But in spite of that, for smaller buildings, passive dash are still the preferred solution. And these are the various components in case of passive dash. So for example, first one is splitter. So it divides the power equally to two or more outputs. Then we have coupler. So coupler divides the power from one input to two outputs with unequal losses. Then we have this attenuators. So this attenuates the signal with the value of the attenuator. Then we have this filter. It is used to separate bands from each other. Then we have this VDA. It amplifies the signals and then rebroadcast. And filter is also called as a duplexer, right? A duplexer is a passive filter component with 3 ports, and it enables the sharing of common antenna between two different frequency bands. Then we have this BDA, which can amplify the signals and then rebroadcast it. And lastly, we have antennas. It receives and transmit the signals over the air, right? Okay. So next is active dash. So active dash is mostly used for large buildings. So active dash need for employment in complex high traffic areas like airports, big hospitals, stadiums, convention centers, and other structures over, you can say, maybe 250k square feet. So imagine we have an infrastructure, a stadium or a building of some sort. So I will use building as an example. Okay. And that building needs some sort of signals, some sort of way of getting signals in and out of the building, right? This may be metallized glass, it may be concrete, right? So these attenuate the signal from outside, right? So if you have tower here, so these signals may attenuate when we reach here because of this metallized glass or this concrete. So cellular signals that might come from some tower or outside reach the building, and then they become much smaller as they go into the building, right? So some sort of dedicated system is needed inside the building to cover the building, right? So with an active dash, you have couple of ingredients. The first thing that you need is a base station or some form of signal source, right? So this is where you will have a base station. So this is here you have this base station. So this base station may be connected to core through the backhaul, but that is not our point of discussion at this moment. Backhaul. Okay. So from this base station, typically you will have a piece of equipment that will call as a head end or the master unit. Okay. So this is the master unit. Any piece of equipment in the form of dash hand and equipment is typically located with the base station equipment. And then throughout the building on various floors, you will have remote pieces of equipment, right? So if you have various floors, then you have this, then we have this remote unit, right? So this is a master unit and this is a remote unit. Some people call these different things, but generically we call it remote units and the master unit. And remote units are far in the field and on the different floors, and master units are the local, right? So now the master unit is connected to the base station by a coaxial piece of cable. So they may be connected through a coaxial cable, right? And there are the RF signals that put into this master unit. The master unit to the RU is typically connected through the optical fiber, right? It can be connected like this. Let me make it yellow because generally in our IB wave design, when I do the design, I use the yellow for the fiber. So then it can be connected to this. It can be connected to this remote unit, right? So these fiber optical cables take the optical signals and move them to the remote. Now at the master unit, so from base station, you are getting RF signal. So RF signal is fed to master unit. So that master unit, those signals are converted into light or the optical signals with the help of fiber and the transport to the remote units. At the remote unit, the reverse process takes place. Additional pieces of coaxial cables are taken with splitters and other devices out to a variety of antennas. So suppose if you have various antennas here, right? If you have antennas, you have antennas, you have antennas, you have antennas. So these RU is connected to these antennas with the help of splitters and couplers. I'm not showing any splitter and coupler, but you need splitters and couplers to join this RU with these antenna, right? So that is why it is called the distributed antenna system, that you have bunch of antennas that are all distributed, right? No surprise here, right? So this way the active dash work at the high level. So we have the active dash. It uses an active component like amplifier, master unit, expansion unit. Okay, so what we need is to continuously amplify signals. So you see here the master unit and the expansion unit and the remote unit. So expansion unit to remote unit 400 meters can be possible, and fiber unit can be up to 6 kilometers, right? So this is our master unit, and this is our master unit, and this is our expansion unit, and these are our remote unit. So this is one example of active dash. So this is RAU5X. So you can say remote performs optical to RF conversion of signals received from the optical interface unit, or OI, and signals are automatically filtered, amplified, and distributed through a external antenna, and uplink signals are then converted to optical signals through and transmitted back to OIU, right? So these are some disadvantages and advantages. So active dash are very popular some installation due to their high level of flexibility, which allows easiest joining. They also have the ability to reach larger distances, and as a result have a greater coverage with the simpler power adjustment, where in some cases they can be controlled through software. Also, optical fiber run exists in many modern buildings, and making it easier to deploy when new in building cells are to be installed. And as far as disadvantage is concerned, it can cause some kind of distortion like intermodulation distortion, and it is very expensive to deploy, and also high hardware cost and high maintenance cost as well. This is what we have talked about. So it has various important components. So like POI, power interface, head and combiners, main unit, optical fiber distribution networks, and the remote units or the media converters. So first of is point of interface. So the point of interface is a variable attenuator used to interface the base station signal, and it attenuates it to the level at which head end can process it. Usually POI are placed in a rack with a wideband combiner inside the head end. So in an IB wave, this can be used to attenuate the signal so that our main unit should not be burned or destroyed, right? Then we have this fiber unit. So all the processed and combined signals will be converted from RF to optical signals in this fiber hub. Then we have this optical fiber distribution. So the optical signal will be distributed to remote units through the optical fiber distribution network. Now, the physical installation, the optical fiber distribution includes splice trays or splice cassettes as well. Then we have this fiber optic cables. You should know all the parts like buffer part, coating, cladding, and the core part. This cladding and core part is very important. And then we have single mode fiber and the multi-mode fiber as well, right? And we have various connectors for this. It can be ST connection, SC connection, LC, FC, MT, and MT. Then we have this remote units that converts optical signal to RF signal and add signal gain that can be adjusted and can be a multi-band, right? And after that, we have this antennas. The RF signal is distributed with the help of antennas. So this is the high-level architecture of antenna active dash. So radio is connected to POI, POI is connected to master unit, and that is connected to expansion unit, and that is connected to remote unit, and then to antennas, right? And lastly, we have this hybrid dash. So hybrid dash is nothing. It is just a combination of passive dash and active dash, right? So first leg, we have this active dash. So for large cables, we use active dash because optical fiber has less loss as compared to coaxial cable, right? And then we have second part as a passive dash, right? So it's combination of active and passive dash. So you can see here one example. So here combination of active and the passive dash, right? So in the beginning, we may have, you can see here at the lower floors, we may have this passive dash, but as we move higher floors with the help of optical fiber, we can have this remotes and we can have this active dash. So here in hybrid, passive and active system can be combined so that we can have advantage of both these systems. So this is passive dash versus the active dash. Let's recall what we have discussed. So we have discussed the evolution of cellular technology from 1G to 5G, right? Then why we need in building? Because there is a congestion in building and capacity issues are there, and most of the traffic, as we discussed, 80% of the traffic is indoors. Then why we need in building wireless? Because 80% of traffic is indoor and building material can be metallized, concrete. So it's difficult to penetrate macro signal inside the building. That's why we need in-building solution. And as you know that there are various important things in our life like water, power, heating and air conditioning. But nowadays, fourth utility is important, that is in-building solution, right? Then various types of wireless solution possible. It can be, we can put more macro towers, cell on the wheels with the help of BDAs, pico cells and femto cells. And finally, we have this distributed antennas system. And we have discussed that DAS can be used in various locations. It may be urban cores, universities, airports, office developments, private public spaces, ports, hotels and theme parks, and the industrial plant. So what is DAS? So DAS is the distributed antenna system, and it has existed since 1980s. And it is mostly, if it is active DAS, then it is a capacity drive, and it can be used in stadiums, airports, casinos, etc. Right? So what is DAS? So radio signals from one or more base stations are fed to multiple antennas and deliver signals with pinpoint accuracy where they are needed. Right? And we have seen DAS infrastructure. It consists of main parts like signal source, DAS equipment, and the passive component. And we have seen various types of system architecture like passive RF distribution, active RF distribution, leaky coax cable, fiber distribution. These kind of things we have seen. In addition to that, we have seen three types of DAS. One is active DAS, one is passive DAS, and one is hybrid DAS. And we have used repeaters also, right? In repeaters, we have talked about serving antennas and the donor antennas. Small cell also we have discussed, right? And we have seen various parts like BBU, expansion unit, and the radio node. We have discussed passive DAS. We have discussed advantage and disadvantage of passive DAS. Their components like antennas, repeaters, couplers, filters, and the cables, right? So these things we have discussed. Also the active DAS just discussed. So all these things we have gone through. And active DAS we have discussed main components are like radio source, POI, master unit, signal distribution, and the remote unit. So again, what is IBS? So in-building solution or the indoor base system or the in-building services or indoor BTS site provide indoor coverage wireless signals by using a series of DAS antennas to distribute this signal inside the office or inside the building. And why we need it? To improve the coverage, to improve the capacity, right? So we have learned that basic overview, then we have learned what is DAS, and then we have learned current and future.